Today we shall be discussing about an important device known as operational amplifier, or in short it is known as OpAmp. So, the OpAmp is basically a device where a number of differential amplifier stages are connected in series, and the overall gain of the OpAmp is made very high, and the OpAmp has a very high input impedance. It is in the order of 1 or few mega ohm, and its output impedance is very small, it is around say less than 100 ohm. So, the OpAmp has a very high gain, but low output impedance and high input impedance. So, this device is basically used in a number of applications. For example, when we want to do mathematical operations in analog, that is, suppose we want to do summation, subtraction, integration, differentiation, etc., then this operational amplifier can be used to have its operation in such a way that we can effectively have these operations performed. That is why basically its operational amplifier name is coming from that it is used to generally effectively do a number of operations like in mathematical operations. But apart from that, the typical applications of OpAmp is to provide a voltage amplitude change, and these voltage amplitude change as well as the polarity. That means, if we want to change the magnitude and polarity of an input voltage, we can use this OpAmp. Similarly, if we want to use this as in filter circuits, for example, we can use this OpAmp to build filter circuits, as well as in instrumentation amplifiers we can use this OpAmp, and also in oscillators. So, these are some of the typical applications of OpAmp. So, the OpAmp symbol is having two input terminals, one is non-inverting and the other is inverting. So, here the symbol of this OpAmp is shown here, input 1 and input 2. These two terminals are there in the OpAmp, where one terminal is non-inverting and the other is inverting, and the output is obtained from the OpAmp, and this is the device symbol. Now, as is seen here, there are two input terminals. So, the voltages are applied at the two inputs. For example, if we apply V1 and V2 at the two inputs, then the output voltage which we will be obtaining, it will be dependent on the difference of the two voltages when we apply the OpAmp in differential mode of operation. That is, the output of the OpAmp in differential mode of application will be dependent upon the difference in the two voltages V1 and V2. So, the output voltage, if we want to find out, we will have to take this circuit of this OpAmp, which is having an input impedance given by Ri and the output impedance is given by R naught. Here basically they are resistances, and the input voltage between these two terminals, which are the input terminals, is the differential input given by difference between the two voltages at the input, that is V1 minus V2 is equal to VD, that is the differential input. If this is so, then the output voltage which will be obtained at these 2 points will be A times VD, because VD is the differential input, it is amplified by A times, A being the OpAmp gain, this A being the OpAmp gain. So, at these 2 terminals we get the voltage A times VD, but then practically an OpAmp has an output impedance, although it is very low, it will be the R naught value will be the value of the output resistance. So, this AVD, a part is dropped in this resistance, and finally what we will be getting at the output V naught is AVD minus this drop. But for all practical purposes, since the OpAmp is having a very high input impedance and a very low output impedance, so we can ignore this drop in R naught. So, practically we can say that the output voltage V naught is almost equal to A times VD, where VD is the differential input, that is V1 minus V2. So, that is the differential mode of operation of the OpAmp. Now, if we consider another mode which is known as common mode, this common mode of operation of this OpAmp will be having the input voltage Vi same to both the 2 input terminals. If this is so, then output voltage will be 0, because this V1 minus V2 is 0, hence V1 is same as V2, same voltage is applied. So, ideally in the common mode of operation we should get a 0 voltage at the output. These two are the basic modes of operation of the OpAmp, and differential mode of operation is that operation where we get a very much high voltage at the output, that is the OpAmp amplifies the differential input, and in the common mode basically we get 0 output if the OpAmp is following all the ideal requirements in the circuit. And what are the basic structure of an OpAmp we will be discussing. Now, the OpAmp has basically 2 input terminals and 2 terminals at the output, where we can apply the voltage at the input side at Vi1 as well as Vi2, and at the output side we can get the output voltage at V01 also at V02. Another mode is that if we apply differential voltage at the input between Vi1 and Vi2, suppose we are applying one voltage, then at the output we can also have the voltage between these 2 terminals, that is in between V01 and V02 we can have the voltage. And so, the different modes of operations of an OpAmp we will be explaining. There can be single ended operation or double ended operation both at the input and output. That means, if we consider the single ended input and also consider the single ended output, then we are applying a voltage at the input which is non inverting. For example, this voltage is Vi, we are applying for example a sinusoidal AC input, and other terminal which is the inverting terminal is grounded. That means, we are applying only a single voltage at the input, and output obtained is at the single end, that is we are getting only at one end, or we are getting a single output at the other side. That means, we are having input 1 and output also 1, single input and single output we are having here. Apart from this, we can also have the other operation where we can apply the input at the inverting terminal, we can make the non-inverting terminal to ground, and we get the single output. That means, you can use one single source either at the non-inverting or at the inverting terminal, and we also get a single output. That is one way we can operate the OpAmp. Another way, we can have a single ended input, but we can get the outputs double ended. That means, we can have two outputs, V01 and V02. This output V01 and the output V02 are opposite in polarity. So, that will be more clear when we consider the internal circuitry, but just now we are just understanding in what ways we can connect the input sources and where we can get the output voltages. So, these are the ways we can have a single source at the input, either inverting or non-inverting, the other terminal being grounded, and the output voltage can be obtained at a single point, or we can have output voltage at both these output terminals V01 and V02, and in this case V01 and V02 are opposite in polarity. Also, another way is that we can apply two sources at the two terminals which are non-inverting and inverting. Like in this case, we are applying Vi1 at the non-inverting terminal and Vi2 at the inverting terminal. So, the differential voltage which is applied between plus and minus terminals at the input is Vi1 minus Vi2, that is the differential input which is applied at the input of the OpAmp. Now, the output of the OpAmp, we have two terminals V01 and V02, where the V02 voltage, if we consider, that will be opposite in polarity with V01. So, what will be this voltage V0 in between these two terminals? If we find out, that will be equal to V01 minus V02, the voltage between these two terminals, and that is nothing but A times V0, A times Vd, that is A means the OpAmp gain multiplied by the differential input. So, here we are applying a differential input and getting a differential output, that is the input is differential because we are having two voltages at these two terminals, non-inverting and inverting. So, definitely the input voltage will be the difference between the two, and that voltage we are denoting by Vd, that is the differential input, and that is nothing but the difference between the two input voltages, and output we are getting also differential, that is the difference between the two output voltages V01 and V02. So, these are the different ways we can have the input sources connected to the OpAmp and also get the output. Now, what is the internal circuit of an OpAmp? What is there in the OpAmp inside? So, for knowing that, the basic building block of an OpAmp has to be understood, that is nothing but a differential amplifier. So, a differential amplifier circuit is shown here. Let us consider this circuit and try to understand its details. So, there are two transistors in this differential amplifier circuit, one is Q1 and one is Q2. Now, these two transistors are perfectly matched, that is their beta values must be exactly equal, and the internal resistances Re etc., which are there inside this transistor must be also equal for both the transistors. That means, the two transistors Q1 and Q2 must be perfectly well balanced or well matched, and this type of matched transistors are used in this differential amplifier circuit. So, we have this Q1 and Q2 which are well matched, two transistors, and the resistances which are connected in the collector for these two transistors are RC, that is also same value RC is to be connected here and here, and there is another resistance RE in the emitters of the two transistors which are connected. If we consider these two transistor emitters, this is the emitter of transistor Q1 and this is the emitter of transistor Q2. So, these two emitters are connected and then it is connected to a resistance RE, and the bias voltages are of course there VCC and minus VEE is there which is connected to RE. These are two NPN transistors we are considering. So, in the OpAmp internally this circuitry is present. So, when we are applying a voltage at the two input terminals, these are shown here Vi1 and Vi2 are the two input voltages connected to the two input terminals, and the output voltages are obtained at V01 and V02 at the point in the collector, across the collector of the transistors we are having the output voltages V01 and V02. So, basically this is the internal circuit, and we will be having a number of differential amplifier stages in the OpAmp. That means, we are considering only a single differential amplifier circuit, but there will be number of stages of this differential amplifier circuits which are directly connected, directly coupled, and the overall gain will be very high because they are cascaded, they are in series. So, after all the cascading stages whatever we will be getting, that will be the gain of the OpAmp. So, it is very high value. Now, if we want to know the operation of an OpAmp on the differential mode, let us consider the operation of an OpAmp in the differential mode, because we have seen that there are two modes of operation, differential as well as common mode. In the differential mode, we have two input voltages and their difference is the differential input. That particular mode of operation let us consider now, and we are considering AC operation, meaning we are applying AC voltages at the input side. Now, as these two transistors are perfectly matched, that is the prime condition to be satisfied. That is why we will be having the same beta value for the two transistors. As well, the emitter resistance of the transistor in both the cases of the two transistors is same. Emitter resistance RE, that is the resistance in the emitter base forward biased junction, will be having the same value. So, if we analyze this circuit under AC, then we will have to draw the AC equivalent circuit for the whole amplifier. The differential amplifier circuit has to be analyzed under AC, and that requires drawing the AC equivalent circuit. So, following the procedure for drawing the AC equivalent circuit, let us try to find out what will be the AC equivalent circuit for this differential amplifier. So, starting from this input voltage Vi1, if we proceed, then this transistor having this base, this is emitter, this is collector. So, the base emitter or emitter base junction will be having the resistance, and that is equal to Ri, if we say beta plus 1 into Re, that will be the resistance between base and emitter. So, the input voltage Vi1, then consider the base terminal of the first transistor Q1, then B beta plus 1 into Re, that is the resistance between base and emitter, that is emitter base junction is having the resistance beta plus 1 Re, that we have earlier derived while discussing the transistor model. So, we are just replacing that equivalent circuit or the model of the transistor. So, the first transistor model is this part, Q1 is having B1, C1, E1 correspond to the transistor base, collector, emitter terminals for Q1. So, between emitter and base, this is the resistance, which is Ri, we are naming Ri just to denote that it is the input resistance of the transistor, and that value is beta plus 1 Re, and we have derived it earlier. This is the emitter point, and the collector C1 is having the current source, which is beta times of Ib1, Ib1 being the current in the base terminal of the transistor Q1, because Ib1 will be dependent on the source Vi1, and on this Ib1 will be dependent on the collector current Ic1. So, that is beta into Ib1 is Ic1, and if we now consider the collector point and look back into this circuit, this collector is connected through Rc, that is the resistance in the collector is Rc, and then as we are considering the AC equivalent circuit, so the DC biasing VCC will be grounded, that will be 0. That means the collector will be connected to ground through this resistance Rc in the AC equivalent circuit, and that is what is happening here. The collector C1 through this resistance Rc is grounded. So, if we consider only this Q1 circuit or transistor Q1 model, then the B1, C1, E1 points give you the model of the transistor Q1, which is having the input resistance Ri, which is beta plus 1 into Re, and the current Ic1, this is the current Ic1, that is beta times of Ib1. And if we consider the E1 point, that means emitter point of the transistor Q1, then this E1 is grounded through the resistance Re, that is clear here, because this E1 point, it is connected to minus BEE, and for AC equivalent circuit this will be grounded. That is why E1 through Re will be grounded, and that is represented here, E1 through Re is grounded. And if we look into the directions of current in the transistor Q1, Ib1 and Ic1, that is the current which flows through the collector resistance, and it will be joined by the base current Ib1 at the emitter point, and the current flowing will be Ie1 beta plus 1 into Ib1, which is equal to nothing but Ib1 plus Ic1. So, this corresponds to transistor Q1's currents. Now, Similarly, if we consider the transistor Q2, the transistor Q2 is having the base, collector and emitter points represented by B2, C2 and E2, and due to this source Vi2, you see here Vi2 is connected as input to the second transistor Q2. So, this base is getting the current due to this source Vi2. This current in the base terminal of the transistor Q2 is Ib2. So, that is shown here. Ib2 is the base current in the transistor Q2, and this current which flows in the transistor Q2 at the collector terminal is denoted by IC2, and the current in the emitter is IE2. The resistance in the emitter base junction for the transistor Q2 is same Ri. For transistor Q1 also it was Ri. So, same value of resistance Ri, since the transistors are matched, same beta value, and that is why Ri is the resistance between the emitter and base, and that is equal to beta plus 1 into Re, and the current which flows in the collector is IC2, which is nothing but beta times of Ib2, and that is the current source which is IC2, and this current flows in this direction through this resistance Rc, because if you look into this resistance, the collector current will be flowing through this Rc in this direction towards the transistor. It is an NPN transistor, and that is why the base current and collector current will be towards the transistor and the emitter current will be away from the transistor. That is why emitter current IE2 is shown by this direction, which is beta plus 1 into Ib2. Now, consider the resistance capital R capital E, which is connected to E1 and E2. The current which will be flowing through this resistance is made 0 by making Re very high. So, in this circuit you assume that the resistance Re is very large, and that is why the current through this resistance Re is almost 0. So, that assumption is made, or we have to basically make this circuit like this only, then we can proceed further easily. By making this Re very high, we are making the current through this resistance almost 0. Now, if we look into the circuit as a whole, we are having two sources, Vi1 and Vi2, due to which there are currents flowing, and so if we consider Vi1 only, making this Vi2 0, we will be having only the currents due to Vi1, and if I make Vi1 0 and keep Vi2 only, then we are getting the currents due to Vi2 only. As this circuit is a linear circuit, we have to maintain that condition intact, that is, it is a linear circuit. Only under the assumption of the linear circuit we will be proceeding to find out the impact of both the sources on the currents flowing in the circuit. That is why, using the linear circuit's property, now we can combine the effects due to Vi1 and Vi2 and find out the currents which are flowing due to both Vi1 and Vi2 acting on the circuit. So, if both are present, then we will be combining the currents due to each of the sources individually. So, the assumption which is to be made now is that the amplitude of Vi1 and amplitude of Vi2 which is greater, because the directions of current when Vi1 and Vi2 both are applied will be dependent upon their magnitudes. If we consider that Vi1 is greater than Vi2, the value of or magnitude of Vi1 is greater than Vi2, then the unbalanced current will be flowing in the direction shown by the red colored arrows, because now we are having the current which is flowing finally due to both Vi1 and Vi2, we are having the currents Ib1 due to Vi1 and Ib2 due to Vi2. These are the base currents. For example, we are considering say base currents due to the two sources. Now, Vi1 is having a base current Ib1 and due to Vi2 the base current flows which is Ib2. Now, when they are acting at the same time, both Vi1 and Vi2 are acting at the same time. So, the unbalanced or the final current which will be left with, that is denoted by say Ib, which is nothing but Ib1 minus Ib2. If we consider Vi1 is greater than Vi2, as the transistors are perfectly matched, so definitely the base current due to Vi1 must be greater than the base current due to Vi2. That is why Ib1 is greater than Ib2. So, the current which will be flowing in a base current, that is base current Ib, overall base current if we are considering, that is equal to Ib1 minus Ib2, which is shown by this red line, and the direction is shown in this because as Vi1 is greater than Vi2. So, finally the current will be starting from Vi1 and it will be flowing in this direction. Similarly, if we consider collector current IC is the unbalanced collector current, say IC is equal to IC1 minus IC2. Similarly, IE is equal to IE1 minus IE2, and the direction of these unbalanced currents are shown by this red arrow, that is IB will be flowing in this direction, IC will be flowing in this direction, they meet together at this emitter point, and total emitter current, that is IB plus IC is equal to IE, then it will be flowing in this direction and then one part will be flowing which is IB and the other part is IC. So, the overall direction of these currents is shown by this red line. So, now we are denoting the final unbalanced currents by the red line. So, the base current which is finally flowing will be IB in this direction, which is equal to IB1 minus IB2, and the collector current which will be finally flowing, that is equal to IC1 minus IC2 is in this direction, both are meeting to give IE which is IB plus IC, and that will be flowing in this direction. Again it will be one part will be the base current IB in this transistor and the other part will be the collector current. So, this will be the finally currents which will be flowing when both the Vi1 and Vi2 are there. Now, we are interested in finding out the voltages at the output. So, V01 and V02 are the voltages that we need to find out. So, what is V01? We can see that V01 is nothing but the voltage drop across RC due to the current flow IC, but it will be minus since current is flowing in this direction. So, IC into RC with a minus sign will be V01 and V02 will be IC into RC with a positive sign, because the direction of current is from top to bottom. So, V naught 1 and V naught 2 are opposite in polarity, but magnitude wise they are equal. So, let us now try to find out, first of all let us find out the base current IB. Now, as is clear in this circuit, we need to apply Kirchhoffs voltage law. So, applying Kirchhoffs voltage law, we will be finding out the base current. So, apply Kirchhoffs voltage law starting from this source VI1. So, what will it be? VI1 minus IB into RI is this drop minus this drop. We are traveling from, starting from the source VI1. So, we will be following this loop up to source V2 and then VI2 and then ground. So, we need to find the Kirchhoffs voltage law in this loop, which is comprising of VI1 and VI2 and then ground. So, this is one loop, this ground and ground they are combined. So, we will be basically having a loop. So, you need to find out the drop in this direction. So, this is nothing but VI1, we are starting from this point, say minus plus. So, VI1, this is actually we are considering in this way, minus to plus is rising voltage, VI1 minus this drop is IB into RI minus this drop is IB into RI again minus VI2 is equal to 0. What is IB? IB1 minus IB2. So, that is what is done here, VI1 minus IB1 minus IB2 into RI minus IB1 minus IB2 into RI minus VI2 is equal to 0. So, simplifying this equation, we get 2 times IB1 minus IB2 into RI, these two are equal to VI1 minus VI2, transferring this to the left hand side, and we are getting now what is IB1 and IB1 minus IB2, which is equal to IB, unbalanced current finally what is remaining in the circuit, that is equal to VI1 minus VI2 by 2 times RI. RI is nothing but the input resistance in the transistor, which is equal to beta plus 1 into RE. RE is the emitter resistance, which is 26 millivolt by capital I capital E, that we know. And now, what is the collector current IC? If we want to find out collector current, IC equal to IC1 minus IC2 and IE1 equal to IE equal to IE1 minus IE2. So, the emitter current finally what is flowing in the overall circuit is the unbalanced current or final current IE, that is equal to IE1 minus IE2, which is nothing but beta plus 1 into IB1 minus IB2, that is equal to beta plus 1 into IB1 minus IB2 we have just now derived. So, this is VI1 minus VI2 divided by 2 times RI, that is equal to beta plus 1 into VI1 minus VI2 by 2 times, replacing this RI by beta plus 1 RE, we are getting this equation. Now, we can very easily cancel beta plus 1 and beta plus 1. Finally, we are left with VI1 minus VI2 by 2 times small r small e. Now, again denoting VI1 minus VI2 by VD, differential input voltage. So, replacing that by VD, we are getting finally IE equal to VD by 2 times RE. After this derivation, now let us go to find out what is the output voltage. Now, what is this output voltage V naught 1, that is minus IC into RC, and that is equal to minus beta times of IB into RC, and IB we have found out, which is nothing but Vd by 2 times Ri, Vi1 minus Vi2 is Vd. So, it is written in this way Vd by 2 Ri. So, Vd by 2 Ri we are replacing and multiplied by Rc. This is V naught 1. What about V naught 2? V naught 2 is equal to Ic into Rc with a positive sign, because the direction of V naught 2 is same as the direction of this drop Ic Rc. So, Ic Rc is positive in this case V naught 2, and which is equal to same in magnitude with this V naught 1, that is equal to beta times of IBRC, and that is equal to beta into Vd by twice Ri into Rc. Now, if we want to find out the differential output voltage, that is the voltage between V naught 1 and V naught 2 terminals, that is in between these two output terminals, if we want to find out the difference in the voltages, that is between V naught 1 and V naught 2, if we want to find out the difference, that is the output voltage, which is the differential output voltage, and that is equal to V naught 1 minus V naught 2, which is equal to simply replacing these values minus beta times Vd by 2 Ri into Rc minus this whole term. So, minus minus it will be minus 2 beta times Vd by 2 Ri into Rc. Now, replacing Ri by beta plus 1 Re, we can simplify with a little approximation, the approximation being beta is almost equal to beta plus 1. Since beta value is typically a high value, so we can very well approximately equalize beta and beta plus 1, and that assumption is effectively used here. So, we are getting finally cancellation of beta and beta plus 1, 2 and 2 cancel out. So, what we get is that the output voltage, which is the differential output voltage at the output terminals of the OpAmp under differential mode of operation, is equal to minus Vd into Rc by small r small e, this Vd being the differential input voltage. So, we can now determine the quantity differential gain. What is the differential gain of the OpAmp, which is Vd, which is AVd, the differential gain of the OpAmp. So, AVd, or we can write AD rather, differential gain. This is the acronym used for the differential gain, A subscript small d, that is equal to V naught by Vd. Take the ratio between V naught by Vd, it is equal to minus capital R capital C divided by small r small e. So, this is the differential gain of the OpAmp, and as we can intuitively see that the value of Re is very small, it is in the order of ohm, but typically the value of Rc is high, that is in the order of kilo ohm or even more than that. So, as a result of this division, we are getting a very high value. Since the denominator is small compared to the numerator, we are getting a high value, that is the OpAmp is having a very high gain in the differential mode of operation. Now, another mode of operation is common mode operation of the OpAmp. In the common mode of operation, we are connecting the voltage Vi common to both the input terminals. So, as you see here, Vi is connected to both the input terminals of the OpAmp. So, in the differential amplifier circuit, if we see, this Vi is connected to the base of Q1 as well as base of Q2, others being the same circuit. So, in order to analyze this under AC operation, let us analyze the AC equivalent circuit. If we draw, the circuit will be similar to the earlier case of differential mode of operation, but here the assumption that Re is very high we are not making, that is there is current flow in the Re, unlike in the previous example of differential mode of operation where we made Re to be very high, so that there is almost zero current in the resistance Re, but not in this case. Now, what will happen is that you are applying the same voltage to both the transistor input. So, Vi is input to the transistor Q1 as well as transistor Q2. That means what? The base current which will be flowing in the transistor Q1 and the base current which will be flowing in the transistor Q2 are same, because the transistors are well matched, perfectly matched transistors we are taking having same beta value, same input source we are applying, so same base current is flowing. The resistance Ri between emitter and base, that is equal to Ri is equal to beta plus 1 Re, and that is also same in both the cases. Rc is connected in the collector of both the transistors, we are having the same Rc. Now, the current flow in the transistor Q1 will be Ib will be in this direction, Ic will be beta times of Ib in this direction. Total current in the emitter of the transistor Q1 is beta plus 1 into Ib, which is in this direction. Now, in the second transistor Q2, similarly Ib will be flowing in this direction, Ic which is equal to beta times of Ib will be flowing in this direction. So, the total emitter current which will be flowing in the terminal E2 or emitter terminal of the second transistor Q2 will be beta plus 1 into Ib. Now, this current is flowing in this direction, which is IE, another I is flowing in this direction, they will be combining and they will be together flowing through this resistance Re. So, the total current flowing through this resistance Re equal to 2 times small I small e, IE due to this part, another IE due to this transistor. So, total will be 2 times of IE flowing in this transistor Re. So, that is nothing but 2 times into 2 times beta plus 1 into Ib. So, now if we want to find out what is V naught 1 and what is V naught 2 at the two ends of the output terminals, let us find out the output voltage. So, what is this V naught 1? That is Ic into Rc, but with a negative sign. Similarly, in this case V naught 2 also will be same Ic into Rc with a negative sign. You mark the difference from the earlier example. Earlier V naught 1 and V naught 2 were opposite in polarity, but now in this common mode of operation IC/Rc is the output voltage which is present at V naught 1 as well as in V naught 2, and they are of the same polarities. That means, this is also minus IC/Rc and this is also minus IC/Rc. V naught 1 and V naught 2 are same. Now, if we use Kirchhoffs voltage law again, let us apply Kirchhoffs voltage law in this circuit. That is, we apply Kirchhoffs voltage law from Vi, this source, and the transistor Q1, and travel through this resistance, again travel through the resistance Re to ground. What we get? Vi minus Ib into Ri minus 2 times IE into capital R capital E equal to 0. So, that is represented here. We are getting Kirchhoffs voltage law given by Vi minus Ib into Ri minus 2 times IE is written as beta plus 1 Ib into Re is equal to 0. So, this is actually Vi minus Ib into Ri minus 2 IE into Re, that is equal to 0. Here this I is represented as beta plus 1 Ib. So, simplifying it, we get Vi minus Ib into beta plus 1, we can take common. What we are left with as small Re plus 2 times of capital R capital E. Here we are representing Ri by beta plus 1 Re. After that we are taking common beta plus 1 Re into Ib, that is common. So, now from this equation we can get what is Ib. So, the base current is given by Vi by beta plus 1 into Re plus 2 capital R capital E. So, this is the base current. So, if this is the base current, we can find out the output voltage at both the terminals V naught 1, which is equal to the voltage V naught 2 and that is equal to nothing but minus IC into RC in both the cases. Polarity of this voltage is plus with respect to ground. Current is flowing from bottom to top with a drop with this polarity plus to minus from bottom to top. So, it is opposite, V01 is minus IC into RC, and here also same case. So, we get that is equal to minus IC is nothing but beta times of IB into RC. We can replace beta IB from the previous expression. So, we get minus beta into VI by beta plus 1 into RE plus twice capital R capital E into RC. So, approximately we can write, after assuming that beta is equal to beta plus 1, this is approximately equal. So, if we approximately equalize, then we can cancel these two terms. So, finally, we are left with approximately an expression which is minus VI by minus VI into RC by small RE plus 2 times of capital RE. So, that is the final expression what we get for the voltage gain in the two terminals of the OpAmp output under common mode of operation. Now, if we want to find out the difference in the voltage V01 minus V02, then we can do that also, as these V01 and V02 are equal. So, obviously, V0 will be equal to 0. So, under common mode of operation, the differential output will be 0, and if we take the single ended voltage gain that we can find out V01 by Vi, if I find out single ended voltage gain, what we have got is this expression. So, V01 divided by Vi will be minus RC by small re plus twice capital R capital E. This is the single ended voltage gain under common mode of operation, and double ended voltage gain is 0, because the differential output V0 is V01 minus V02, and that is equal to 0. So, finally, we have got to an important conclusion that if we want to find out the common mode voltage gain of the OpAmp, which is the double ended output voltage, with respect to double ended output voltage, if we try to find out the gain, that will be 0, because output voltage between the two terminals under common mode of operation is 0. That is one important aspect of OpAmp, because if we have a voltage which is common to both the inputs, then if the transistors are well matched and the resistance RC is exactly same for both the transistors, we ideally should get 0 voltage. But that sometimes does not happen, because it is very difficult to get exactly matched transistors having the same beta values and the input resistances, etc. And also the value of RC in both the resistance in both the transistors which are connected at the collector side are rarely exactly equal. So, because of this difference in the resistances in the two transistor collectors, that is RC is not exactly equal and the two transistors are not exactly matched, because of this fact practically we do not get a 0 voltage under common mode operation. Even a very small voltage you get in the common mode of operation. That is because of this fact that if the transistors are not well matched and RC1 and RC2 is not exactly equal, then AC, that is the common mode gain, will not be 0. So, in this analysis whatever we have found today is differential mode gain and common mode gain, and these two are the two basic gains which we will be dealing with very frequently. So, this analysis today what we have done is about a very important device in electronics, that is operational amplifier, which is a cascaded amplifier. The individual units of this cascaded arrangement are differential amplifiers. So, a number of stages of differential amplifiers are cascaded to finally give a very high amplification or gain, and this OpAmp has input impedance very high value, but output impedance is very small. The OpAmp is basically used in a number of applications, starting from mathematical operations in analog computers, as well as filter circuits and instrumentation amplifiers and oscillators, and different combinations of these circuits are used to get our desired operation. Basically, we apply OpAmps for a number of operations, including mathematical ones, and those applications we will be discussing in our next succeeding lectures. But the basic idea of the OpAmp is that we have two operations or operating modes, differential operation of amplification as well as common mode amplification, and in common mode application the ideally output voltage should be 0, and in differential mode of operation we get a very high output voltage, and we will see later that in practice we get a number of applications of this OpAmp, and we will be discussing those applications and we will be finding out what mathematical operations can be performed with the help of these basic OpAmps.